All right. So, sorry this has taken a while to get to this, but today has been a day. All right. But it was a good thing. Ironically, it has to deal with photons and the solar array and some exciting things that will be happening with that. So we're going to finish up chapter 25. We got one assignment out of that. And I'm going to send you that out, and I'm going to send you the answer key for it. And this is where we start to get into some kind of weird stuff. Okay, so just accept it, move on, it works, don't question it. So we're going to actually start with hopefully what you know. So let's say that you've got a conducting hoop, and you're going to move the north end of a magnet into that hoop. Okay, so the magnetic field is coming out of the north, okay, and you're going to create an influx of X's. So nature goes, oh, okay, we can do that. Then we're going to create more O's to balance that out, which means the current is going to be going in a counterclockwise direction like this, okay? Easy peasy. So here's what's important, and this is going to be the key. If you change a magnetic field, okay, the whole key to this is if you change a magnetic field, then this creates a change in the electrical field. So one of the great mysteries, if you look at the history of science, was that how energy got from the sun to our little rock. So one of the things that they thought was that this energy, because it traveled as a wave, had to have a medium. So just like sound can't travel through a vacuum, it has to have particles of nitrogen, oxygen molecules, something. It has to have a medium through which to transfer it. So they thought the same thing had to happen with the sun. So for a while, here's a quick history lesson. They thought there was something called an ether, okay? And this ether had this weird, mysterious properties, like the Earth could move through it, but it never slowed it down, and it didn't in any way inhibit the light. But we needed a medium through which this energy could get from the sun to our rock, because they didn't think it could be a vacuum. So what James Clerk Maxwell came up with, okay? And if you ever study enough physics, you'll run into Maxwell's equations, okay? And James Clerk Maxwell was the first one and he did this late 1800s. He was the first one to really come up with a mathematical way to treat light and what it was. So here's the odd thing, and this is why we don't need this ether, is that if you go back to the magnet analogy, is that and just accept this, don't flip out and go, what do you mean? Okay, just accept it. So what this means is that this is going to happen whether there's a loop or not. Okay, so in other words, when you change a magnetic field, you induce a change in an electrical field. You don't have to have the loop to do that. Okay, so anytime this is going to happen, you can change the magnetic field, that's going to induce a change in an electrical field. So what I tried to draw here, and this is tough to draw, but let me kind of explain what I've got. So imagine that you're looking at this three-dimensional view on end. So any electromagnetic wave, and hence the term electromagnetic, has an electrical field to it, and this is what I was trying to draw with the purple line like this, okay? So this purple line like this is like the electrical field. Then at right angles to that in the horizontal plane, then you've got a magnetic field. So what happens is that if you create a change in the electrical field, then that's going to create a change in the magnetic field. And then if you change the electrical field here, that creates a change in the magnetic field. So what that did is that eliminated the need for the ether, because this electromagnetic wave basically becomes self-propagating. You don't need a medium through which to transmit it like you do sound, because the change in the electrical field automatically creates a change in the magnetic field. So this is what Maxwell did, is that he was the one that came up with this whole treatise about how to explain this and treat this whole thing. Now, one of the most important things about what Maxwell did, he came up with this equation. So this V is the velocity of an electromagnetic wave. And when I mean electromagnetic, I mean any type of electromagnetic wave. Could be visible light, radio waves, X-rays, doesn't make any difference. Any electromagnetic radiation, he predicted, and this is the whole key to this, he predicted a velocity. So this is 1 over epsilon naught. Epsilon naught, remember, is the vacuum permittivity constant. And that's 8.85 times 10 to the negative 12 coulombs squared newtons per meter squared. Multiply that by mu naught, which is the vacuum permeability constant. Okay, these are not the same thing. Okay, but this is one of the rare instances where you see them both in the same equation. So basically, they came up with these numbers, okay, and 4 pi times 10 to the negative 7 teslas meters per area. And if you really want to challenge, do the dimensional analysis and prove that you get velocity out of all of that. That's a tough one. But anyway, so he actually predicted the speed of light out of this equation before we actually measured it. So he said, okay, hey, this is what the speed of light is. Now, that plays an important role with Einstein, because once they actually began to measure the speed of light, they noticed that it remained constant, but that gets into relativity, and we'll get into that later. Now, I'm not going to expect you to memorize this. I'm just throwing this out here as like general background knowledge that you need to know of science, okay? Now, here's the other thing. So the other thing he came up with is this equation. So basically what this says is that the electric field is going to equal the speed of light multiplied by the magnetic field. So the speed of light is obviously a constant, okay? So what this means, as the magnetic field becomes stronger, the electric field becomes stronger. If you decrease the magnetic field, you decrease the electrical field. So if you were to draw like a graph and you were to put the electric field on one side and your magnetic field on the other, oddly enough, the slope of this line would get you the, wait for it, speed of light. So as your magnetic field becomes stronger, your electrical field becomes stronger, and that's what increases the energy of the system. Okay, now, all you have to know is that these are like constants. Here's the speed of light. If you increase your electrical field, you increase your magnetic field. Now, old school, this is stuff that you've seen before. This is just a quick refresher. So what you have here is that you've got speed of light, lambda times frequency. I always learned it as C equals lambda nu, okay? So the old joke, what's new? C over lambda, okay? It's an old joke, but go with it. So, and again, these two, what this means is these two are inverses of each other. As you decrease the wavelength, you increase your frequency, because these two together multiplied always have to equal the speed of light. Okay, now, when you talk about power and intensity, and again, this is kind of a refresher of what we've done. So remember, intensity is power divided by area, otherwise known as watts per square meter. So obviously, as if you have a smaller area, you're going to have a more intense situation. So like if you're this is why if you're standing very close to a flashlight and you stare at it, guess what? You're really, really close to it. There's not much area, because that area is going to be 4 pi r squared. And remember, this is the area coming out like in a sphere. Okay, like here's the sun, and this is radiating out like this. So you get watts per square meter. As your radius is smaller with the same power, that's going to increase that intensity. Now, the other way to look at power or intensity, let me finish this up. And these are obscure equations that are in your textbook, and they're not on your equation sheet. But let me kind of explain what these are. So this first one, the way that you can calculate the intensity of a wave, if you know the value of the electric field, then that's epsilon naught squared, or excuse me, your electrical field squared times epsilon naught times the speed of light times 1/2. That also equals, if you know your magnetic field, okay, then you've got 1/2 C divided by epsilon naught B squared. This is your magnetic field. So depending upon what you're given, these are these equations. And no, in no way, shape, or form am I going to expect you to memorize these equations. But here's what I am going to expect you to know, is that as you increase your electrical or magnetic field, that increases your intensity, okay, which is how X-rays work. Okay, now, here's the other way that you can look at power. So power you'll see this written as NE over time. Because now, N is the energy, N is your number of photons, okay? E is your energy per photon. So if you look at this, then you get joules per second, okay? Otherwise known as power, because it's energy per unit of time. So your energy per photon comes out of this equation, E equals HF, which you all have seen before. Old school, you have E equals H nu. Okay, so what's new? E over H. That's the other version of the joke. Now, H is Planck's constant. I always memorized it as 6.626 times 10 to the negative 34th joule seconds. Your book actually, or your equation sheet actually listed as 6.63 times 10 to the negative 34th. It's a rounding thing. I'm old school. I use this. I don't care which one you use. But again, here's what's most important. As your frequency increases, your energy increases. Now, look what happens with the units. This is joule seconds. You're going to multiply that by frequency, which is 1 over seconds. The seconds are going to cancel out. You're going to be left with joules. Hey, we're off to the races. Now, the other way that you can do this is that because C equals speed of light equals lambda times frequency, so if you take the speed of light and divide it by wavelength, you get frequency. So the other thing that you can do is that you can do a little trickery here and take this and slam this in for frequency, and that's where you get HC over lambda. So there's 3 ways that you can calculate your energy. You can use HF, you can use H nu, you can use HC over lambda. I don't care which one you pick. It just depends upon what you're given in the problem. Now, let's talk about electron volts. Electron volts are a measure of energy as well. So, and we've talked about, we've done this before. Remember, an electron volt is the energy given to an electron, hence the term electron volt, as you move across 1 voltage of difference. So, 1.6 times 10 to the negative 19th joules is equivalent to 1 electron volt. So, what you can do is, and this is where this is handy, and you'll see where this plays out later on, is that sometimes you'll see Planck's constant, instead of written in joule seconds, sometimes it's handy to use this number. So this is 4.14 times 10 to the negative 15th electron volt seconds. All I did was I took Planck's constant, divided it by the equivalent number of joules in an electron volt, and I got this value. So let's say that you have a wavelength of 600 nanometers, and you want to find the energy in 1 photon. So I'm going to show you 3 different ways you can do this. I don't care how you do this. This is up to you. Now, if you're a purist, if you are an absolute purist, you're going to go, oh, HC over lambda. Here's Planck's constant. Here's the speed of light. Remember, nano means 10 to the negative 9th. You're going to multiply these 2 numbers together, and you're going to get 600 times 10 to the negative 9th as your wavelength, and you're going to get your energy that way. Okay? If you're old school, boom, there you go. The seconds cancel out, the meters cancel out. Miracle of miracles, you get joules, you're off to the races. Now, here's another option that you can do. And this is on that yellow sheet that you have, that AP Physics 1 equation sheet. If you want to shortcut this and multiply, have a value of h times the speed of light, then if you take Planck's constant, multiply that by the speed of light, you get 1.99 times 10 to the negative 25th joule meters. Okay, so the seconds cancel out and you get joule meters. Then you still have to take the nanometers and change that into meters, and you get, oh, that got weird, and you get this, okay? So this is another way that you can do the problem. Now, if you go and, oh, Bergkamp, I like electron volts. Oh, good, I'm happy for you. So the other thing that you can do is that you're still going to use HC over lambda, and this number is also on your sheet. So this is 1.24 times 10 to the third electron volt nanometers. So with this one, you don't have to convert the wavelength into nanometers. You can just leave it as this. The nanometers will cancel out. Your answer is left with electron volts. Okay, so I don't care how you work this problem. This is up to you. So just figure out kind of what method is going to work best for you, and you figure it out. So I'm going to send out the assignment. I'm also going to send out the answer key to that. The calculations aren't horribly difficult, but the next assignment tomorrow, that one's going to be due. So this is just kind of an introductory thing. This is the end of chapter 25. And there you go, kids. So